Okay, let's see, south and north. Okay, so if we move south, our potential increases. Okay, so here's north. I'm going to make this the positive direction, and south, that'll be the negative direction. Okay, if we move ourselves 15 meters, it increases by 45,300. So this could be at 0 volts. This could be at positive 45,300 volts. Okay. So what this means, by the way, is that we're moving toward positive charge, right? If our potential is going up, we're moving toward positive charge. So these are our horizontal plates. Let me just say it looks like this. We got positive charge down here. Now don't confuse the positive charge with the directions, right? Okay. This up north is a positive direction, south is a negative direction. But if our potential goes up by 45,300, it's very simple. We're going toward positive charge. We're going to a place where it's more positive. Okay, like Gresham. It's an old joke. I don't know if you'll get it. All right, so let's see. Your electric potential increases. What is the magnitude and direction of the electric field? All right, let's just see which way it is, okay? By the way, the electric field is going to be positive. Okay, due to this picture, right, we know that a positive charge is going to feel a force up, okay, away from where it's more positive, right? But let's just see if the maths works, right? So our E should be the opposite of change in voltage over delta R. And this is our electrical, right? So let's take that 15 meters and we go down. Let's just go with that, okay? So it's the opposite of our change in voltage is that if we do this, if we go down 15 meters, is that we actually go up 45,300 volts. Okay. Our delta R, though, is negative 15 because we're going down on this thing, right? And so therefore it's going to be a positive electric field, which of course we knew that it would be up, but you know, there it is. So 45,300 divided by 15 is 3020. And the negative cancels the negative, and so you end up with positive 3020, and that's volts per meter, or newtons per coulomb. Either one is just fine. Okay, and then it's going to be up our map. Up our map is toward north. All right. Okay. Personally, doing all this stuff with the signs, I lacked the patience and diligence to do that as a student. I would draw a picture like this because that picture makes more sense than the maths. Okay, let's see. What is the math? Okay, if moving a charge 3 meters to the north increases the potential energy of the charge by 48 joules, what is that charge, and is it a positive or negative charge? Well, think about this. If we're increasing, if we take some charge, if we take a positive charge and we move it to the north, it desperately wants to go to the north. We'd actually do negative work on it. But here we're doing positive work on it. So if it's something that doesn't want to go north, it must be a negative charge, right? A negative charge is going to be like, oh, don't take me there. All those electrons, keep me away, right? I mean, never anthropomorphize charges, though. They hate that. Okay, so let's do the maths here. I'm sure we'll get a negative number here. Okay, so we're going to move the charge 3 meters to the north. Okay, and we increase the potential energy by 48 joules. So that's by the way the work, right? So the work is equal to the Q times the change in electrical potential, right? Okay. But let's figure out what the change in electrical potential is, right? So ultimately we're going to use that, but first we have to use this guy. E is the opposite of change in voltage over R, right? So therefore our change in electrical potential is the opposite of E. Whoops. Let's supposed to be an E, times the R, okay? So let's figure if we move ourselves 3 meters up this picture here, right, then our change in potential is going to be, it's going to be negative, but let's see why it is. The opposite of our electric field, right, 30-20, which is positive, the opposite of positive, 30-20, right, times, and then if we move ourselves, remember we're moving ourselves to the north, so that's our positive direction, right? This guy was negative, positive 3 meters. And so if we do 3 times that, we get, is that just 90-60? 3 times. We go negative 90-60 volts. Okay, so now we can do this. Charge is just simply going to be, charge will be, what will it be? It'll be work divided by change in electrical potential, right? So it's 48 joules, that's positive 48 joules, divided by negative 9060 joules per coulomb, right? This will end up being coulombs, right? Okay, so 48 divided by the number I just got. I'm getting negative 0.005298 coulombs, which is 5.30 millicoulombs. Remember, a milli is times 10 to the minus third, right? Like milliliters, millimeters, millipedes. That's 1/1000th of a pede. Okay, millicoulombs, and it's negative, sorry. Okay, because we divided by a negative number. Okay, let's see, what is that charge? Is it positive or negative? What force does that field exert on the charge? Oh, dear Lord, okay. We can do this. Force, E is F over Q, so therefore force is EQ, is positive 30-20 newtons per coulomb or volts per meter, either one is correct, times negative 0.005298. All right. And I get negative 16 newtons. So 16 newtons south. Is that the right answer? Yeah, there we go. 16.0. Whoops. Oh my gosh. There it is. By the way, there is yet another way to do this. Okay. It said what is the force exerted on it, right? Isn't that funny they came out to something even, right? Here's why, because remember, work is also force times distance, right? So 48 is equal to force times, and then the distance was 3 meters. You forget it all in the whole, right? So 1/3 of 48 is 16. That also works. Lots of ways to do this. Old formulas, new formulas.